Hey there, it's ChemGal, and in this video, I'm going to talk to you about HNMR, which stands for Hydrogen Nuclear Magnetic Resonance Spectroscopy. So let's say you're in a laboratory, and let's say that you made a compound, but you don't know what the heck you made. Well, what you can do is put it in an HNMR spectroscopy machine, and it's going to give you a type of graph that looks something like this. So each compound has its own HNMR graph that corresponds to it. That is, that no two compounds have the same HNMR graph. And it usually goes up to about 12 ppm. On the y-axis, you're going to have what's called intensity, and we'll talk a little bit about that later. Towards the left of your graph, you're going to have what's called downfield. And towards the right of your graph, you're going to have what's called upfield. Let's say a signal appears on your graph in this region, downfield. We would say that that signal is going to be more de-shielded. And if a signal appears towards the right of the graph, that means that the signal is going to be more shielded. And I want to take a moment to point out that the graph, the x-axis, increases going from right to left, which is not like most graphs you've seen before. Now, what does it mean to be de-shielded or shielded? And what's a signal? So let's say you have a compound, and in your compound, you have some sort of hydrogen in there. So if there's a hydrogen in your compound, it's going to give rise to a signal. Now, hydrogens, are they typically delta positive or delta negative? We know that hydrogens are typically going to be delta positive, and that was my attempt at drawing a delta sign. If your hydrogen is attached to an oxygen, the oxygen is going to be delta negative, and the hydrogen is going to be delta positive. Now let's say that your hydrogen is attached to a carbon. So now your carbon is going to be delta negative in this case, and your hydrogen is still going to be delta positive. We call this, by the way, a dipole moment. Which atom here is going to be more delta negative? Is it going to be the oxygen or the carbon? To help you answer that question, you might want to think about which atom is more electronegative. Well, we know that oxygen is going to be more electronegative. So let's make a little note of that here. Oxygen is more electronegative. For comparison, we can say that carbon is actually less electronegative than oxygen. So what does that mean for the hydrogen? Well, remember I told you how this is a dipole moment? Well, what's happening here is there's a bond between the oxygen and the hydrogen and the carbon and the hydrogen. And remember that each bond contains a total of 2 electrons. So in this bond, there's oxygen donating an electron and hydrogen donating an electron. And in this bond, there's carbon donating an electron and hydrogen donating an electron. Look at OH, for example. What's happening when we say that the oxygen is going to be delta negative, that means that the oxygen is going to be pulling on those 2 electrons more than the hydrogen is. This oxygen is hogging those 2 electrons tighter than the hydrogen. That means that the hydrogen doesn't have as much electron density because oxygen is tugging on those electrons. And so we say that the hydrogen is more delta positive. We also can say that the hydrogen is more de-shielded. Now the same thing is going on for this carbon and this hydrogen over here. However, we took note that carbon is less electronegative. Well, there's 2 electrons here and carbon is tugging on them, but who's tugging more? Is carbon tugging more or is oxygen tugging more? Oxygen is tugging more on those electrons because oxygen is more electronegative. And so both these hydrogens are still going to be delta positive because there's less electron density for them. However, this hydrogen over here is going to be way more delta positive than this hydrogen over here. So let's make note of that. This hydrogen is going to be more delta positive because it's attached to a greater electronegative atom. And this hydrogen is going to be less delta positive than that hydrogen because carbon is less electronegative. And so if we compare those two hydrogens on this graph, this hydrogen is going to appear more downfield and it's going to be more deshielded because it is very delta positive. Whereas this hydrogen is going to appear more upfield because it is less delta positive. It's attached to a less electronegative atom. So if we were to compare those two hydrogens, we would say that this hydrogen is going to be way more delta positive than this one. So now let's go ahead and draw the HNMR graph that would correspond to this structure. So here we have drawn 2-butanone in condensed form so that we can see all of its hydrogens. And first we want to determine how many signals does this structure have. Well, we see that here we have 3 groups of hydrogens. 1, 2, 3. And each of these are going to produce a signal on our HNMR spectrum. So we're going to go ahead and call this signal A. We'll call this group of hydrogens signal B, and this group of hydrogens signal C. So we have A, B, and C. And what we're going to do is figure out all the information for each of these signals. So signal A is composed of 3 hydrogens. Signal B is going to be composed of 2 hydrogens. And signal C is going to be composed of 3 hydrogens. And what we want to do is determine the chemical shift of each of these signals. So let's go back to the handy-dandy list we made earlier, and let's determine the chemical shift for signal A. Now, signal A is a CH3 group, and if you recall, a CH3 group has a signal around 0.9. Now, remember that the CH3 group is attached to an R group, which is any alkyl group. And we see here that this CH3 group is attached to this guy. And there's some business going on over here, right? We got some oxygen, we got some carbons. And so we see that this R group is pretty electron withdrawing. So remember I told you that we shouldn't be so fixated on these numbers because yes, this number can be 0.9, but because the R group has a lot of business going on, it might be around 1 or even 1.1. So we're going to go ahead and guesstimate that the signal would be around 1 ppm. Now let's go ahead and skip B for a moment and move on to signal C. Signal C is our perfect ketone signal. And over here we see that when we have a ketone, our ketone hydrogens are going to give us a signal around 2.4. Now I want to go ahead and take it a step further and let you know that ketones tend to occur between ranges of 2 ppm to 3 ppm. I like to call this a ketone region. And sure, other things can pop up here too, but mostly you're going to see some ketones. So signal C is a perfect ketone, and we might see this signal early on, maybe around 2.1 or 2.2. So let's go ahead and write that in. We'll see it around 2.1 ppm. Now, if we compare this to signal B, yes, signal B is coming off of a ketone, so it is going to be within the ketone region. However, it does have a little bit more business going on because it also has this extra methyl group over here, and that's also electron withdrawing. So we might see this not early on in the 2 region, but maybe closer towards the 3 region or the middle of the 2 to 3 region. So we might see this signal around 2.5. So you see here how the chemical shifts are very sensitive to the atoms around it, which is why I told you don't be so fixated on specific numbers, but think of it more as approximations of where the chemical shift would lie. And so now I want to talk to you a little bit about splitting. And you might have noticed that when you have a signal on your graph, it looks a little funky, right? If your signal looks like this, that means that it's a singlet, and we typically draw it as an S. If your signal looks like this, your signal splits, and we say that this is a doublet, and we typically call that a D. And if your signal splits this many times, it's going to be a triplet, and your signal is going to be called a T. And if your signal is a quartet, your signal is going to appear like this, and it's going to be a Q, and it goes so on and so forth. Now, if your signal splits 5 times or more, we call this a multuplet, and you might see it as M for multuplet. Now, each of our signals is going to split differently, and to determine that, we use something called the N+1 rule. So let's go ahead and figure out what that means. So if we want to go ahead and start off with signal A and apply our N+1 rule, we have to think of N as our neighbors. So N is your neighboring hydrogens. So let's go to signal A. Over here we have our signal A. And what we want to do is go to the neighboring carbon. And we ask ourselves, how many hydrogens does this neighboring carbon have? We see here that this neighboring carbon has 2 hydrogens. So our N value here is going to be 2. So let's go ahead and insert 2 for N. So it's going to be 2 plus 1. We're going to get a total of 3. So our signal is going to split and become a triplet. So signal A is going to appear as a triplet on our HNMR. Let's go ahead and try this out for signal B. So signal B is right over here. And remember that we need to go to our neighboring carbons. And here we actually have 2 neighboring carbons that we need to reach out to. So first we can go to this neighboring carbon and we can ask ourselves, how many hydrogens does this carbon have? And this carbon has no neighboring hydrogens, so we can ignore it. What about this carbon? This carbon has 3 neighboring hydrogens. And so our N value for signal B is going to be 3. So we're going to have 3 plus 1. And this is going to give us a value of 4. And 4 is going to give rise to a quartet. So signal B is going to be a quartet on our HNMR graph. Now what about signal C? Take a moment to try signal C on your own. For signal C, we're going to look to our neighboring carbons. So if we look here, we have 1 neighboring carbon, and we can ask ourselves, how many hydrogens does this neighboring carbon have? It has 0 hydrogens, and therefore our N value has to be a 0. So we're going to have 0 plus 1, and that's going to give us a value of 1, which means that we are going to have a singlet. And we abbreviate that as an S. So signal C is going to appear as a singlet on our graph. And now that we have this information, we can actually sketch what our HNMR is going to look like, which is pretty fantastic. So let's draw out our HNMR. We'll number it going from 0, and we don't have to go up too high because our highest signal is 2.5. Intensity is going to be on the y-axis. So now let's go ahead and plot this out. Signal A is going to appear as a triplet at around 1 ppm. So over here we can draw out a triplet. Signal B is going to appear as a quartet around 2.5 ppm. And signal C is going to appear as a singlet around 2.1 ppm. So let's go ahead and label those. We have signal C, signal A, and signal B. And signal A has 3 hydrogens, signal B has 2 hydrogens, and signal C has 3 hydrogens. Now let's take a moment to talk about why each of these came out in different shapes and sizes. So there's actually something called the integral. And for those of you who might have taken calculus, you might be familiar with this. And I promise it won't be that scary. The integral is the area under the curve. And so with HNMR, the integral is actually going to be proportional, and I'll draw this alpha symbol for proportional, to the amount of hydrogens in the signal. All that means is that signal A, which is composed of 3 hydrogens, should have more area under the curve than signal B, which has 2 hydrogens. So the area under the curve is proportional to the amount of hydrogens you have. Now let me ask you about signal C. Would the area under signal C be greater or less than the area under signal A? That's a trick question. The area should actually be the same, and give yourself a pat on the back if you caught that. And of course, I haven't drawn these to perfect proportion, so please don't go ahead and measure it out. But theoretically speaking, if you put this compound in an HNMR spectroscopy machine and you got out an HNMR graph, the area under signal A is going to be equivalent to the area under signal C. And the area under signal B is going to be less than the two of those. So give yourself a pat on the back for drawing out this HNMR graph. So that's it for this video. If you liked it, please leave a thumbs up and feel free to subscribe. Happy studying!